Now that we've reviewed the model, let's see if we can go through the results one by one. So, quick review: the simulator, the results, and the results warehouse are all together on one spreadsheet. In terms of results, we actually have a list of items here, and we'll quickly walk through this list step by step, one by one. So if you look at the Black-Scholes equation, if you go through the Black-Scholes equation has two pieces. The first piece is S of n d1, sorry, S times n of d1, which is the expected present value of the asset that you would receive if the option is exercised. Second piece is x e minus r t minus t into n of d2, which is the expected present value of the strike price if the option is exercised. So the idea is you will receive the underlying asset if the option is exercised, and if the option is exercised, you will pay the strike price. So the present value of the strike price is given by strike times the PV factor times ND2. The PV factor because the payment, the exchange that happens at expiry, happens at maturity, and we have to include the impact of time value of money. So the first cell that we look at, XPVF into ND2, basically comes through the PV factor times the strike price times ND2. So now the question is, where does ND2 come from? If you look at ND2 here, if you just do a quick trace, ND2 here comes from a count, and this count here comes from this table. Now, what is this count? This count, if you remember correctly from the introduction to the model, is simply the track of all the instances when ST was greater than X. So if you look at these results, let me clear this. If you look at these results here, you can see that the first cell, the first iteration is 7.9, the second is 9.2, the third is 9.6, and the fourth bingo is 10.1. Yep. And it's this iteration here that counts as 1. If you go through the sheet, scroll down, go through the sheet, that's 1, 2, 3, 4, 5, 6. There are 6 instances when ST, the final price of the underlying security, was greater than X. These 6 instances are counted and stored here in this cell, and I simply divide this 6 by 30 to get the probability of ST being greater than X for one set of 30 iterations run by our Monte Carlo model. So coming back to this calculation again, all we're doing is we're saying take the PV factor, multiply by the PV factor by the strike price. That gives me the PV of strike. Now the only thing I need, which is missing, is the probability of the option being exercised, and that is ND2, and that comes to me from this table. So store the logical test, the results of the logical test being ST is greater than X, sum those, divide them by the number of iterations, and you've got your ND2 estimate. Now with ND2, the second piece that we need to look at is ND1. So where does SND1 come from? SND1 is simply the first half or the first part of your formula for the price of a European call option using the Black-Scholes equation, and that represents the expected present value of the stock that you would receive if the option is exercised, and the option is exercised if ST is greater than X. So if I trace the result, I get the SND number from here. Where is this SND number coming from? Before I go into where is this SND number coming from, let's look at a slightly alternate calculation of SND1. The alternate calculation of SND1 is in this cell. So that's where we start. So the first question we have to answer when we look at the alternate calculation is, what is SND1? SND1 is the expected present value of what you would receive if the option is exercised. So to calculate this, we need 3 pieces. The first piece we need is, what is the expectation of ST if ST is greater than X? So if you remember, when we first spoke about this, in this column, we have all the values of ST irrespective of whether ST is greater than X or not. Alright, so where do we start with ND1? What is it? What is SND1? SND1 is the expected value of the asset that you would receive if the options exercise at some future date in time, which basically means that you need a couple of pieces. The first piece that you need is what is the expected value of ST when ST is greater than X. So this is a conditional expectation. It's an expectation of I'm only interested in those values when ST was greater than X, and I'm only interested in that value at maturity at time t. So before you do ST or expected value of ST when ST is greater than X, you have to look at how do we calculate expected ST. So expected ST is simply the sum of this table that you see here. And if you look at this table is simply the value of ST that comes out from our simulation model. All we do is we sum it. So here's the current iteration time 0. We sum it and we divide it by 30, which is the number of iterations, to get a value of 9.12. That's ST. Now for ST, given ST is greater than X, we need to see if ST is actually greater than X, and we actually have 1, 2, 3, 4, 5 and 6. We have 6 instances where ST is greater than X, and to get ST when ST is greater than X, we simply sum this and divide this by the number of instances to get the value of ST when ST is greater than X, right? So this is what you would get if ST is greater than X, and that number is given here, which is 10.39. Where is this number coming from? This number is coming from the same cell here. Right. Now let me remove the arrows. Now, so what we've done is we've said we now have EST, ST is greater than X. We also have expectation of ST. When will I receive this amount? I will receive this amount only when the options exercise. So for that means I need to calculate the probability of ST greater than X. That probability is our old friend ND2 that we've already calculated. So if you multiply these two pieces together, ND2 times expectation of ST when ST is greater than X, you get the expected value of the asset that you would receive if the options exercise. The only piece that is missing now is the fact that when you receive this payment, it'll be a year from now, which means that we have to add in one small factor for time value of money, and that factor is given here. So if I go to the next cell, which is simply this calculation times the present value factor, I get my answer 2.06. Now this 2.06 is the same as SND1 here. So what we've done is we're still working within the Monte Carlo framework, but we have two ways of calculating SND1. One way of calculating SND1 is here in column cell. What we've just done is we've walked through the second way of calculating SND1, which is through an intuition, and that intuition is only using results from the Monte Carlo simulation table that you see on the right hand side. So we've covered X into PVF into ND2, which is the result or the expectation of what you would actually end up paying when you pay the strike if the options exercise. We've also calculated SND1, which is what would you actually receive if the options exercise. Now let's look at ND2. ND2 we've already covered. ND2 is simply the count, the number of instances when ST is greater than X, and that count divided by the number of iterations, which are 30 in total for a Monte Carlo simulator. ND1 is simply SND1 divided by S. So that's the alternate technique or the alternate mechanism. If I have SND1, I can simply divide that by S and I find out ND1, which then gives you an interesting translation or interpretation or alternate meaning for ND1. If you look at SND1 as the expectation and you divide that by S, then what does that mean? What does that represent? And we'll come back to that either in our PowerPoint presentation or when we conclude this course. So if you have these pieces, what is the value of the call option? The value of the call option is just the difference between these two pieces. Okay. And where do these pieces come from? So I have two pieces here. I have piece 1, which is simply the difference between 2.06 and 1.98, and I have piece 2, which comes from the table, which is here. So if you look at piece 2, this is piece 2, there you go. Piece 2 is coming from this side. Now how is this piece 2 calculated? This piece 2 is simply, you see this cell, call premium current iteration. This cell is max of st minus x comma 0 times the PV factor. So this is one path, this is one iteration. For every single iteration, I calculate this value. For every single iteration, after I've calculated this value, I store this value here. And then when I complete my simulation, I simply take an average of this to get my premium, which is 0.08. For this specific iteration, we're very lucky because we can see that the call premium that we've calculated using Monte Carlo simulation is a little short of the call premium that we calculate using the exact closed form formula equivalent for the Monte Carlo for using the Black-Scholes equation. And this is the same this is the same as the premium that we've calculated using an alternate technique and an alternate plan. So if I were to take a step back, what you've done is you've calculated the value of the Black-Scholes equation using Monte Carlo simulation using two separate techniques. The first is plain simple Monte Carlo. And that plain simple Monte Carlo simply calculates the value of the payoff based on the iteration. So you get the ST from your path, from this path, you get your ST from here. ST minus x comma 0, max of st minus x comma 0 times the PV gives you one value. You store this value here, you run your simulator, the simulator generates 30 iterations, you take the average of this number and you have a result, and we call this, let's just call this pure MC. The second method is an intuitive method that also uses the same results, but it does not calculate the value of the call option directly. Let's call this the indirect method. Let's call this indirect MC. Okay. Now the indirect MC is actually an indirect implementation of the Black-Scholes method using Monte Carlo simulation. And if I look through this results, these values come from here. This value comes from a difference from between this one and this one, which is SND1 minus X PVF into ND2. And then for each of these pieces, ND2 comes from this table, ND1 also comes from this table. For ND1, the expectation is actually driven by the expected value of ST when ST is greater than X. And we compare that value with the expectation of ST, the unconditional expectation of ST, and we can see that it's always higher. We take that, multiply that by the probability that you will actually exercise and take possession of the security, which is our old friend ND2, multiply that by the discount factor, and we get the net value, which is 2.06, which is the value of the premium, right? Sorry, which is the value of SND1, and that's what gets plugged in here. So both values are equivalent, and the only reason and rationale for doing this and for building this way was to explain the difference between ND2 and ND1. And the primary problem that we face is that understanding ND2 is easier. Understanding ND2 is simple because ND2 is simply the unconditional probability of ST being greater than X. ND1, on the other hand, is difficult. ND1 is difficult mainly because it has a conditional element. And given the context of the Black-Scholes equation, sometimes it is difficult to follow that conditional expectation. I hope what we've done here in the last two sessions help explain how ND1 and ND2 are different from each other. And it also shows or shares how using Monte Carlo simulation to walk through the Black-Scholes model builds a much more stronger intuition for understanding the formula than anything that I've done, at least personally, in the past. And finally, it also shows the primary difference between the two expectations, the unconditional expectation of ST and the conditional expectation of ST when ST is greater than X. I hope you've enjoyed this session. Thank you very much for your time. This is Jawad Ahmed Fareed for FinanceTrainingCourse.com. This video has been brought to you by FinanceTrainingCourse.com. For a number of additional similar courses, training materials in PDF file format, sample Excel files, and models, please see FinanceTrainingCourse.com. Thank you.